Well, thank you very much. I think we could organize for this fantastic school. It just came yesterday by talking with some of you. I understand that it's been really exciting, and I hope I can provide a nice material and action for you.
By the way, if you want to carry the mask, as a speaker, you can.
So yeah, better like that. For me, it's a pleasure to be here. This is the first time I'm talking in a not online talk since the start of the pandemic restrictions. So it's a special moment for me too. And also a little bit of a challenge because to talk about, to give a review as wide as this one about actions is, as I always say, it's a bit challenging because, as you will see in a moment, it's a very dynamic subfield of particle physics. Many things are happening, so it's always difficult to give a fair account of everything. And also the level of the format is new to me. I'm used to give a lot of seminars about actions and action experiments during the last years, but to talk a bit about theory, cosmology, I will say something about astrophysics also. And of course, experiments over 4 sessions like this one is a new format to me. So I hope I will do a good job. And I put some effort in preparing this material also with for the notes that you already have. And of course, you can stop me at any time and ask questions. I will try to answer. I must say that I am experimentalist. I'm going to talk about theory at the beginning, about cosmology, but my field, let's say, of expertise is experiments. Nevertheless, I don't fear to talk about theory because I sometimes feel that for some type of students, an experimentalist talking about theory is quite helpful because we tend to focus on not the technical details, but on the implications of the different aspects. For those of you that are more theory oriented, probably you will not get fully satisfied probably with what I'm saying, but for that reason, I have included a lot of references in the notes. You will see it's intensely populated with references, so you can pick up whatever you need to look more in depth. In particular, some reviews. I've used mostly a couple of reviews. One of them by myself together with my colleague Javier Redondo. That's already 2-3 years old. But another one which is more theory oriented, also very recent, is a very good one. You have them in the notes and also in the oops. Well, first of all, what I plan to talk about during these days is, of course, a bit of theory to understand the motivation of actions. And then I will move quickly to cosmology because the reason why we're here is because actions are very good candidates to compose the dark matter, and we'll explain why is that. Then I will talk a bit of astrophysics. This is because, contrary to other dark matter candidates like WIMPs, actions being such light particles, they may have a strong influence in some astrophysical scenarios, mostly the evolution of stars. And this can be used to constrain action properties very strongly. In fact, until recently, there were the most important results on the action couples. Most of them came from astrophysics. Only recently, experiments start catching up a little bit with this. And also there are some possible hints of the presence of action from astrophysics. So I think it's a nice ingredient in any action review to talk a bit about astrophysics. And finally, I will focus mostly in the third and fourth talk on action experiments, on action detection. And you will see also that in this part of the classes, why it's so challenging to talk about action experiments is the typical action experiment is very different from the typical particle physics experiment. And we touch a different combination of expertises from quantum technologies, X-ray, astronomy, many different expertise that are not typically present in particle physics groups. This is also a challenge, but at the same time, is an attractive feature from this field, and it offers a lot of opportunities for new groups, for new people, for the new generation also to make an impact in this field. There is a lot of room still for new ideas, for new experiments. Still, some of them at relatively small scale, which is something very appealing in particle physics. In particle physics, we are used to huge experiments with many collaborators, and this is not yet the case in actual physics, not always. Okay, this is what I was already saying before about the bibliography. You have many references in the notes, so you are invited to consult them. And if you have any questions, you can also ask me offline. And if I'm not able to answer you properly, I can direct to the right colleague, paper, whatever. And just want to stress a couple of reviews that I have used for the notes. This first review is more focused on detection, although it also includes other aspects. And likewise, the second review from Lecture1 is more focused on the theory and phenomenology, although it recounts also a little bit the experimental efforts. Some other nice references which include some of the material I'm using, but in a wider context. So it's nice to see how actions are presented in this report that has been very recently prepared by a group of people as a mandate of APEC. APEC is the Astroparticle Physics European Committee, the funding agencies, and it makes a review of all the efforts that are mostly European but also worldwide ongoing now to detect dark matter, and also actions are presented in this wider context, which is it suits also this group. And finally, there is also this other review in which actions are presented in the context not linked with dark matter, but of searches for new field interacting particles in general. And then I also mentioned this textbook, but it's not yet available. It will be soon available. It's also a nice reference because it's a bit more pedagogical, including also exercises and things like that. So it's very interesting. So let me start by a very brief anticipation of the main messages that I plan to convey during these lessons. So I'm somehow anticipating the conclusions. Actions are motivated by theory, mainly because they represent the most compelling solution to the so-called strong-city problem that I will describe in a moment. It's an issue of the standard model that is not solved, and the most compelling solution includes the Pichai-Quinn mechanism. This is where actions were first proposed. Then the paradigm of the action has been extended beyond this, and now people talk about action like particles, which are not necessarily linked to the strong-city problem, but they appear very often in different extensions of the standard model. In particular, now it's well known that string theory automatically produces a lot of predicts the presence of a lot of these fields in the theory. For many, most importantly, and it's the reason of this tool, actions may solve the dark matter problem. So they are very good solution, good candidate for dark matter, like the case of WIMPs. And they are not, they were not created to solve dark matter, but they do. So that's why it increases the motivation of this model. Astrophysics, in the case of actions, may also give precise information on constraints or hints of this particle. I will say something about this. And most importantly for experiments, the relevant parameter space of these particles is, at least a good fraction of it, is at the reach of current technology, not for detection, current or near future technology. And this is something very appealing to put efforts into experimental lines. So let me start with the theory without going into details. The strong civil problem is what first motivates the action, and why is that? So let me say a few words about this. So the Lagrangian of the QCD contains, or may contain this famous theta term, which is something that is, do we have pointer?
Yeah, both laser and later.
Traditional. Let's take it. Do you see the pointer?
Yeah.
So this is a term that is okay, this is the theta parameter, which is constant from the standard model. So if we admit this is part of the standard model, then you need to postulate the value of this input parameter. And this is the gluon field. The gluon field is dual, and this term is CP violating. So in principle, probably you may not have heard of this term, and this is because being a total derivative term has no effect in perturbative calculation. So it's usually not relevant for many calculations of this fundamental. So people even tend to ignore it. When one writes the full Lagrangian of the standard model, many times it's not written, it's not even written. But it has observational consequences. In particular, it predicts an electric dipole moment for hadrons, in particular for neutrons. Can be estimated, something okay at this level. And the important thing is that for values of the order of, this is an angle, by the way, so this is an angle. So for values of the order of 1 for this angle, my expectations of a new parameter based on the model, you have values of the electric dipole moment of the neutrons that are should be.
Maybe raise your mic maybe because they don't hear anything.
Better like that? Can you hear me?
Yeah, I have a quick question, and that's fine. Thanks. So this is maybe an obvious question, but why not just combine that theta parameter into our strong coupling constant? Like, why not make them one parameter? Does theta appear somewhere else in the Lagrangian where the strong coupling constant does not?
No, this theta parameter only appears in this term. It does not appear in all the other sectors of the Lagrangian where the strong coupling constant appears. So you
Okay, I see.
cannot really
And-
do that.
Yeah, and why is it necessary for this gluon term?
It's not necessary. One could say, I ignore it, and the standard model works. But if you let me continue with the next slide, this is not a appealing situation.
Okay, thank you.
So from the non-observation of this prediction of the neutron dipole moment, you can constrain the value of this theta parameter to very low value, so something of the order of 10 to the minus 10. So why this value is so small? So one could, as you said, okay, then it's not necessary. You just ignore it and it does not exist. Maybe some reason that we don't know yet prevents the presence of this by some symmetry or whatever. Well, this, if you see the QCD Lagrangian isolation, okay, you could maybe do that. And this theta parameter is connected with the vacuum of the vacuum of QCD. But when one considers the QCD Lagrangian in the full standard model, then you cannot avoid that the electroweak sector contributes also to this type of term, and then this theta parameter in reality should be seen as a contribution of two, one that would come from the QCD itself, and one from the electroweak sector, and this is something connected with the quark mass matrix. So in principle, the fact of requesting that this term does not exist, or is very small, as small as 10 to the minus 7, implies that this sort of two contributions should cancel, or should cancel each other to such a level, which is something very implicit. So basically, the essence of this transient problem is why this angle is so small, given that in the standard model comes from two completely unrelated origins. So the most elegant solution to this problem is what was proposed by Vichy and Quinn already quite some time ago in the 70s. And since then it's called the Vichy-Quinn mechanism. So basically, they postulated a new symmetry in the standard model. This U1 symmetry that is since then called Vichy-Quinn symmetry. That is spontaneously broken as an energy scale Fa, which is one of the most important new parameters of any action model. So as you will see now, it's not predicted by theory; it's a new scale that you postulate. So you have the typical mechanism that you probably know of symmetry that is spontaneously broken. So you have the presence of a new number-Walsh composition. You have this type of potential for a Higgs-like field. What is this Higgs-like field? It depends on the particular way you implement this mechanism in the standard model. It's not important now. So, but you have this potential when the energy scale drops below this new scale Fa, it becomes a typical Mexican potential, so that the vacuum of the theory, the value of this Higgs field, the radial mode gets a non-zero value, a vacuum expectation value. And then the angular value, it takes a random value between 0 to 2 pi, and then the vacuum of the theory sits in a place where it breaks this Vichy-Quinn symmetry. So then you have this degree of freedom, this angular degree of freedom, that is the number-Walsh composition, and we are going to identify this with the action field. So it's a new field in the theory. Why this solves the strong problem? Well, because one can see that in the Lagrangian, by doing this, you create this new term, which is very similar to the theta term, but with the difference that you have the gluons, and instead of a constant, we have now a field. So this basically this A here, which is going to be the action field, is this angular degree of freedom that appeared in the stream before. So basically, this absorbs whatever value we had, whatever constant value from the theory we had before in the definition of the field. One can redefine this constant into a field that now depends on the coordinates. So in other words, the theta parameter is rendered unphysical by this mechanism. It doesn't have any physical meaning anymore. And more than that, this new field has a potential due to QCD effects. So it's not postulated in the mechanism. It's the QCD itself that what makes is following this picture is like tilting this Mexican half potential, and therefore not every value of this angular field corresponds to the same potential energy. So it has a preference for one particular point. So the theory tends to give a value to this field that turns out to be the right value to make this angle CP conserved. So the CP conserved. Yeah.
Does that field can it still be broken into the vacuum structure part and the quark mass matrix part? Do those two, like how we broke it into those two parts, can the field also be decomposed?
No, this is like a constant. So this is absorbed by the field.
So I guess I'm wondering how. I sort of understand why we sort of need both of these parts in our theta parameter, but qualitatively, aren't those two parts still important? Is it important that we have a vacuum structure piece and a quark mass matrix piece?
In fact, it's not important. All this becomes unphysical in some way.
Okay, maybe could you describe a little bit more what you mean by unphysical, please?
Well, it doesn't have any consequence. At the end, you have these terms. If the Vichy-Quinn mechanism is there, what matters is that you have something like that. This sort of disappears because you can redefine this this field, including a constant level. So it doesn't enter in any computation anymore. So it's so for all practical purposes, it doesn't exist anymore. It's done. What you have now, it is only.
Great, that helps, thank you.
So the city conservation now is obtained in a dynamical way. So you have this field taking, due to this potential, taking the right value. So you don't need to postulate it anymore, like was in the case with the theta term. So you get it dynamically. So that's the two features of this mechanism that makes the strong problem, solving the strong city problem. Okay, so something that was not, I mean, Lecture1 were focused on solving the strong city problem, but they didn't care so much for the consequence of their own proposal. And it was later on Weinberg and Wilczek that realized, okay, this is a real new field in the Lagrangian that has its quantum perturbations can be detected as particles, and they identified and they dubbed this field as the action field. In fact, it was Wilczek who proposed action as the name, because it did not clean up the civil problem. So it was based on a soap detergent. This is not a joke. He himself mentioned this in his Nobel Prize lecture. This is true. What is nice is that the original paper from they work independently. There are two papers, one from Weinberg, one from Wilczek. They both realize the same thing. Weinberg proposed to name this field the Higgs-led, which in some way I sort of like, especially when the Higgs was detected and experimentally detected, and something for Higgs is like gymnastic system. But nevertheless, this didn't stay with people. Took the proposal from Wilczek and it's been called action since then. I'm talking about papers that were written in the 70s. So this is 40 years old, all these ideas. So we have a new particle in this Lecture1 standard model, and this particle, by the way it has been introduced, it inherits some basic properties. So it's important to know some of these properties are linked to the Lecture1 mechanism. Some others are not. So there is some freedom to how to implement the Lecture1 mechanism in the standard model, and this gives rise to so-called action models. Depending on the action model, the action may have different properties, but some of them are basic that they are given by the Lecture1 mechanism. So the action is a pseudoscalar particle, it's a neutral particle. It gets automatically a very small mass, and this is linked with the fact that we have this potential. So even if at the very beginning, when the Lecture1 symmetry breaks spontaneously, the new degree of freedom, the Moog-Olson, that degree of freedom represents a massless particle. But then when the temperature goes down to the QCD and the QCD effects become relevant, then the action gets a mass. And this mass is a full QCD effect, so it can be calculated, and this is something like that. Of course, we have always this dependence that you will see it in all properties of the action. All the mass and all the couplings of the action are always inversely proportional to this energy scale, this Lecture1 scale. So at the end, this means that we have no idea what is the mass of the action. If someone tells us what is the value of this F, then automatically we know what is the mass of the action. And it's a stable particle for all practical purposes. In reality, it's not strictly stable. The action can decay into two photons. You will see that this is a very important property, the coupling of action to photons. but the decay constant is longer than the life of the universe, so it's a stable particle for particle processes. And as I said before, all the phenomenology of the action of the couplings will, as you will see in a moment, are inversely proportional to this FA. So this Pacheco scale will drive the phenomenology of the action.
Sorry. Thank you. So it's kind of surprising to me that we couldn't observe photons and determine that, or sorry, not photons, pions, and determine that FA scale. If the axion is getting its mass through the mixing with the pions, couldn't we do some kind of observation or experiment or something to determine FA? I guess I'm not appreciating why that's so difficult experimentally.
Well, you can. There are some experiments that are proposed to that you can see this effect. But if you go to, so in fact, originally the original proposal of the action, they identify this new scale with electroweak scale, and this gives rise of phenomena like similar to what you are saying that should be seen in accelerators, for example, and they were not. So this third generation model was soon ruled out because of this reason. Now the trick was to make the models a bit more slightly more convoluted, disconnect this from the electroweak scale. So now in all realistic models of actions, this new scale is much higher than electroweak scale, and this drives all these couplings and the mass of the action to very low values, and all these effects are not strong enough to be seen.
Got it. Thank you.
That's why now, I mean, they were called invisible actions. Now all models are invisible actions, so we don't anymore use the word invisible. We jump already to the next.
Sorry, so can you say, so is it correct to say then that the mass is given by the slight tilting of the potential which you have mentioned at the beginning, which is essentially you define a minimum, and this is where you get the mass from?
Yes. So the slight tilting potential is a way to see. It's a graphical way to see this. Basically, you get the same thing. You have a.
These are right from which you see the corrections to this original picture where essentially it will be flat.
Yeah.
Okay, thank you.
So that's what I just said. No? The originally proposed actions were this new energy scale was identified with the electrode scale, but this was soon ruled out because it would lead to effects that should be seen in accelerators, and they were not. So the second generation of actions, they were dubbed back then as invisible actions because they were thought that they would not be possible to, they could not be detected. They were so weak coupling constant. Well, time has passed, technology advanced, and now we are in a position that we think we can see this invisible action. We don't call it invisible mode. So there are many action models, and recently it's a renewed area of work for phenomenologists that create new action models. But the most famous ones, the oldest ones after the very original reshaping and wider Lecture models, are these two, and they are now seen as two families of models, not just single models. And most of the modeling effort can be linked to this one of these two families. So very briefly, the KSVZ actions, the letters come from the authors that first proposed them, are based on usually the standard model is extended with new heavy quarks, at least one, maybe more, and one single complex scalar Higgs that is what implements this scheme that I just mentioned of spontaneous breaking of the PQ symmetry. And okay, this is the most simple ingredient, but more complex generalizations of this are possible. And the important consequence, the important feature of these models is that they do not feature a coupling to electrons, and that's why sometimes they are called hadronic actions, because they only couple with hadrons And as you will see with photons, the photon coupling is present in every model, basically. The other category of models are the so-called DFS actions. In this case, there are no exotic fermions added to the standard model, but the fermions of the standard model are assigned some charge, some PQ charge, so some way to interact with them, to transport with the new symmetry. There is 2 Higgs doublets added to the standard model and 1 single complex scalar Higgs that is what implements the mechanism of the spontaneous breaking. There are a couple of variants, at least, and then there are, of course, more convoluted models based on these ideas. And the important thing is they do feature a coupling to electrons, and they are sometimes called good actions because this scheme is sometimes motivated in the framework of grand unified theories. It's nice. So the way the particular model that you pick up to implement the action in the standard model fixes the remaining phenomenology of the action. So you go from very generic properties. The gluon coupling is the basic ingredient. You cannot change that. This is the essence of the PHA queen. This is present always. This induces a mass. This is also something generic, but of course it depends on this unknown scale. Then you have the photon coupling, which is also predicted by every action, but with some particularities. There is some model dependency contribution there. And then you have fermion couplers that may be completely absent, like in the case of electron coupling. That some models do not have electron coupling at all. Some models they do have it. Or nucleon couplings, you have nucleon couplings in principle you have in every action model, but there is a lot of model dependency, so you could have cancellations of components. So it may also be suppressed. So, for example, action photocoupling, which is going to be the most important coupling, I will be presenting this in all my following slides, and is the coupling on which most of the action detection strategies are based. Not all of them, but most of them. So just to have some definition that will be used in the following slides. So effectively, the action photon coupling is represented like that. So this is the photon fields, and this is the coupling. Sometimes this coupling is the dependency with the F is explicitly stated in this way. So this coupling can be seen as a dimensional coupling divided by this FA. So sometimes I will be using the C's, or you will see the C's in many papers. Sometimes you will see the G's. Both are all action photon couplings. This has dimension of G to the -1, energy to the -1, and these are dimensional. So the model dependencies here can be seen inside these C's here, and basically they are equal to this is the model independent one and the model dependent. This E over N are discrete numbers from the model. So the electromagnetic anomaly and the color anomaly numbers of the model. For example, for the KSDZ, this fraction is 0, and for the DFZ, this fraction takes the values 8/3 or 2/3, depending on which model. And for more generic versions of these models, these can take different values. But it's difficult that this compensates and cancels with the non-model independent part, which is fixed to this 1.92, which is usually difference. So this leads to the very famous QCD model band that you probably have seen on the talks from actions, and you will see in many of my plots. So I will not escape on this because they will come slowly through different lessons. But basically, this is where most of the action phenomenology or detection activity plays a role. It's not all the story because it's only action photon coupling here, this axis, and this is the axial mass. So As you see, the action photon coupling is inversely proportional to the F, the known energy scale of the pH, and the same happens with the mass. So this means that the coupling is inversely proportional to the mass of the action. So a particular action model will be represented in this plot by a line, and you have here this orange line. This is the case. This is action model, and where in this line is the action will be fixed by the value of the energy scale. This effect. That's why one particular model in this plot is one line, and you cannot really play too much with these basic models. Under some generic assumptions, this fraction should be constrained within this range, more or less, and this fixes a set of lines which are represented by this yellow band here. So this is a very important theory target for experiments. So we want to explore this region of the parameter space. This is where the conventional QCD action models lay in this problem. I will come back to explain the rest of the items, but I want to fix the main feature of this problem. Of course, word of caution. This is a let's say a conventional picture, but theories and phenomenologies are very active recently, and there is more recent implementations of the pH mechanism, the standard model that are able to populate this plot with QCD action. So when I put the word QCD before actions, because sometimes actions are used in a loose way, including also action-like particles. So when I say QCD action, I'm referring to the original definition of action as coming from a pH mechanism. So this QCD action can be implemented in ways that give rise to models that live outside this yellow band. This is a plot from practical model that was presented in some conference, just to illustrate that there are many things also happening at the model building level, and I will keep referring always to this yellow band, but one should not be too strict with this and be prepared to the possibility that you may find actions also outside the yellow band. This is of course very interesting for experiments, because you can imagine that to push the sensitivity of experiments that are at the moment represented basically by these yellow regions and also these green regions here. To push these so many orders of magnitude down to the yellow band is very challenging thing, but this been addressed anyway. So before moving to something else, some few words about all the couplings that are not the action photon coupling that are also relevant, but I will be very brief. We have also action nucleon coupling. This is also, in principle, there is a model independent prediction from the group coupling, from the pH mechanism, but it is mixed with many model dependencies. So basically, you have effective terms like this one. You have the action coupled with fermions, and again you have this C A fermion coupling divided by the F, and this C contains model independent terms that are fully defined by QCD, like for the proton you have this, for the neutron you have this, but also you have model dependent terms which depends on the way the individual fermions of the theory, the different quarks are how the specifics of the action model is defined. So you have all this number here, and you can imagine there may be some cancellations. Typically, it's difficult to cancel both neutron and proton couplings at the same time, and they have some typical values. For Kaiser, you said, for example, the CA with any quark is 0. It's not the case for the DFS model, and then you have many more models with different values. For the case of the action electron coupling, the situation is a bit different. Again, you have the same type of term, which is always also expressed in this Yukawa way, which is equivalent for our purposes. And again, you have similar to the different in the action photocopying, we had defined the G and the C, and both are referred sometimes as coupling. The same happens with the action electron coupling. And I stress it because I will be saying something about this action electron coupling. So the difference with the nucleon coupling is that, as I mentioned before, the action electron coupling does not have a model independent contribution. So the action electron coupling exists only if your particular model predicts it. So it's not a generic necessity for any action. So for example, KSB set actions do not have action electron coupling. However, the FS set actions they do feature. And these are the particular predictions for these C's here for the action for the electron case. For the case of this particular model, the FS1 and the FS2, where this beta is the ratio of the two vacuum expectation values of the two Higgs that are in this model.
Good question. Do the DSFZ models also include couplings to the other electrons or just electrons? Do the DSFZ models include couplings to the other electrons or just electrons?
To the other electrons?
To the other leptons.
To the other electrons. In general, I think yes.
Okay.
But then the most important regarding observational consequences are the electron coupling.
Okay, thank you.
There is a question in the chat.
Yeah.
Which says, is any of the models, ESFZ or ESFZ1, preferred over the others and why?
No. They are all for example, there are considerations that they are subjective. For example, the DF set is motivated by grand unification theory. So if you are a fan from grand unification, that maybe you may prefer this one over the other. But in general, there is no preference. I would say no strong preference. So, and there are more couplings that I will not mention because they are commented very briefly in the notes, and you have more reference that you have couplings with pions that are important and in some cosmological considerations, but more related with quantum matter, for example. And there are also other terms that link to the existence of neutron electric dipole moment, for example. And some superviolating couplings. Well, there is some literature about this now. Let me move to things that are that have been connected later on with experiments. So I will be focusing most of my time on the action photon coupling. So the fact that you have this sort of coupling, action photon photon, means that actions interact with electromagnetic field and convert into a photon. This gives rise to this famous action photon mixing, which once you fix this external magnetic field, typically is a magnetic field, in general electromagnetic field, but typically is a magnetic field, you have this phenomenon of action photon mixing, which is the formulation is very similar to the neutrino oscillation. So actually the actions oscillate into photons and vice versa along the propagation, the line of propagation inside the magnetic field. And this is used in many of the experimental strategies that will be presented later on. So you have an action, and this if this interaction happens coherently over a macroscopic field, magnetic field, we have these typical oscillations from actions into photon in such a way that the probability of the initial action to be seen as a photon after a given length can be expressed in this way that it will be probably be familiar to you. So basically, you have an oscillatory term on the length, on the length propagated here. So the L is the length propagated, and then of course you have the mixing term, or something related with mixing term here, which for the case of an action is the action photon coupling times the magnetic field that triggers this conversion, the external magnetic field. So this formula will appear in different forms when we deal with photon action detection experiments. Okay, this is not the most general formula. There are a number of approximations that have been used to reach, like 1D propagation, small mixing, and relativistic velocities. We'll come back to this a bit later on. And then before moving to cosmology, I wanted just to stress that all what I have said so far applies to QC reaction. So this is the most motivated member of a wider family of particles that sometimes referred as action-like particles. And it's not clear the precise definitions. Some people define action-like particle in different ways. So a phenomenological definition closer to the experiments, we start using the word action-like particle once you build an experiment that is sensitive to actions via the action photocoupling, for example. Then of course you want to extract as much physics as possible from the experiment. So if such type of experiment would be sensitive to any particle that has coupling with the photon, not necessarily the action, the QC reaction that comes from all this scenario that I just described. And there are many extensions of the standard model that are not necessarily linked with P-chain mechanism, but predict this type of particles that couple to photons. Of course, there are other definitions in the literature. Sometimes they are referred to weakly interacting sub-EV particle, which a little bit in connection with the good name. That one would see as a bit wider than what an arc is. And as I mentioned before, a typical example that for some people is important, so for some other people that are not so fond of string theory, it's not really important, that string theory predicts this type of fields in a very, in fact, many fields, we see. So this is just to mention that, okay, sometimes people talk about action-like particles, and of course, these do not have the constraint that I mentioned between the coupling and the mass for the case of an action model. So you could, in principle, populate all this plot with this type of problems. So you make an experiment and you don't reach the yellow band. You can always say, okay, this is interesting if you explore a part of white space here, because you may have halves there, or you may have this more exotic using the action we mentioned before. Yeah.
Hi. So
hello. So for all these QCD axions, right? You have different models, and they should all lie in that yellow band roughly. But there is a limit to how light they can be, right? This QCD axion. So this yellow band doesn't extend forever, like downwards, right? So how does it look like?
Well, in principle, it does extend to arbitrarily low values, but of course, at some point, they become less from the standard QCD action picture. They become less interesting. There are some, because the scale, the energy scale that corresponds to such low values is so high that you reach the blank scale. So it may be not so motivating to have an action model that requires a P-chain scale that is the blank scale. And also there are other constraints. If you go to very low, you will see when I start talking about cosmology that action production as dark matter is inversely proportional, roughly inversely proportional to the mass. So you have, for a particular model, at some point, if you go to very low values, you have overproduction of dark matter. You can evade this constraint by, I will talk about this later on.
Okay, cool.
So you're gonna really see that there is a sharp bound, but the interest of very low QCD action masses fades away with
Okay, as an I'm an experimentalist, so I'm just, because I always see this yellow band, and I'm just curious about how hard humanity has to search before we can like exclude QCD axions.
It's a very
That's
good
my big
question.
observation, yeah.
if you really aim to exclude
Okay,
completely,
yeah. Over, yeah.
then it's gonna be great
Oh, okay.
because you can always invoke you can always invoke the cancellation also in the induction photon coupling and put actions here. It will be even harder. You can also, okay, most of these I will explain experiments later on, but most of these green regions are experiments looking for action dark matter. This is not the case for the blue region, which looks for action from the sun. So this has been excluded only under the assumption the action is the totality of dark matter. So it may happen that the action exists, but it's only a fraction of that matter, in which case all these green regions should be scaled up. So if you really want to exclude the existence of actions, be it a matter or not, it's a hard thing. It's going to be a very hard job for humanity.
Okay, well, thank you.
So I see this region here for the masses from 10 to the -6 till, I don't know, 10 to the 2, 3, whatever. Now, why can't we, or which experiments could exclude this region of the parameter space? Why is it so, I mean, where are the
Which region?
So
This one?
sorry, this white region between the yellow line and the green dots from the, yeah, exactly.
Well, this is very hard. I mean, experiments, the easy experiments are up here and the more complicated experiments try to go down. So if you ask me why you cannot go down, well, because we don't have yet such a technology. We are pushing this down. So this is and the goal is the yellow one. So nobody has invented an experiment that is able to detect actions here, because let's start first with this one here, which are easier. So it's an iterative process, but maybe I have a lot of things to say about experiments, so maybe
Okay, so
on Wednesday we can discuss all this.
Okay. So it's issue of technology. Okay, so
Yeah, and maybe just one more question over here. But I was wondering, some of these experiments, it seems that they're flat lines, like these flat dotted lines. How are they equally sensitive to all masses?
That's the nice thing of these experiments. It's almost a flat line. At some point, it goes up. And I will explain this
Okay.
later on.
Okay, thanks.
So I can trust this group, no? to be aware of the. Yes.
We have half an hour.
No, I move now to cosmology. So maybe it's a good time. If you have more questions so far, you can ask them now. But so you probably are now very well aware of the standard picture of how thermal relics are produced in the early universe. And now the first question that should come as a surprise is how the action is such a good candidate for dark matter if it's such a light particle. We're talking about masses, as you saw before, below the electron volt and typically much below the electron volt. So in principle, the typical the standard picture of thermal relics that are they produce a freeze out density of particles due to the expansion of the universe, it works also for actions, but the population that is produced by this is, of course, relativistic, and therefore this does not solve the dark matter problem. It's similar to the case of neutrinos, it produces a hot dark matter component, which may be interesting also, but it's not why we say the action is a good dark matter candidate. And in fact, people can use this to constrain the mass of the action. The fact that hot dark matter is produced leads to a upper bound on the mass of the action of the other electron volt. So actions of the other electron volt produce hot dark matter in quantities that start being in tension with cosmological observations. I think that the latest limit is 0.5 electron volts. So this is somehow the maximum mass one typically considers when we talk about action physics due to this effect. For ALPS, this would not apply because this is using phenomenology of the action, like happened to pi and things like that are not necessarily present for a generic ALP. So you could go for heavier ALPS, but not for the case of the action. Anyway, the important thing is not this. The important thing is that the Pechequin mechanism itself offers a non-thermal production of non-relativistic action, and that's why we say action is very good. All dark matter can not only is a hot dark matter candidate, but it's also not hot dark matter. It has nothing to do with the typical thermal production of rakes in the early universe. And I will try to explain, which is basically a repetition of what it says. It's basically the same Pechequin mechanism that I mentioned, but it's actually realized in the universe when, since the very beginning, when the universe had very high temperature to the polar time now. So again, we have this potential for this Higgs-like field, which is like that for very high energies, for very high temperature. So very early in the universe, we didn't have an action. The action appeared as a physically relevant degree of freedom when the universe is cooled down below Fa. The problem is that we don't know when this happened because we don't know the value of this transition, this energy scale. So, but when this happened, then suddenly you have this change in the shape of this potential, and then you have this new degree of freedom in the universe. So you have actions only then appearing as a massless particle. So we don't have just this tilting that I mentioned before. So at this time, the action was massless, and you have actions everywhere in the universe. And then when the universe keeps cooling down and reaches the QCD temperature, then you have this tilting of the potential. The action starts only then feeling the mass, feeling the curvature of the potential, and then whatever was the value randomly chosen by the action field at the Pechequin transition, it typically was not the minimum of the potential when the potential starts getting formed, and this is called the misalignment or the realignment effect. The action starts rolling down to the minimum from whatever it was to the minimum of the potential after the transition, the second transition to through the QCD temperatures.
Will Hubble friction affect the evolution of that field the way that it's rolling?
Yes. So I'm telling a very simplified cartoon, but this, of course, this has to be taken into account. This happens in a expanding universe, and in fact, this falling from this point to the minimum happens with some effective friction due to this Hubble expansion and so on.
And are there models in which that Hubble friction could essentially stop the slow roll or pause it for some amount of time at a non-minimum value?
Yes, there are a lot of convoluted models. playing with this. Yeah.
Thanks.
I cannot give you more details. But,
No worries, thank you.
so what happened at the end is that you have at some point in the life of the universe, the action mass is switched on, and then you have this field over the universe that start oscillating with an amplitude that depends on this misalignment, this initial angle that is a random value. So it's another free parameter of the theory in some way. I will develop this more later on. And it fills the universe with this energy, which behaves like all dark matter. This is highly non-relativistic actions permeating the universe, and with energies that will depend on this initial value, and therefore they can be the energies, the densities necessary to explain the matter. So this is called vacuum realignment, sometimes also called vacuum misalignment or axial misalignment. The question is this producing the right dark matter density? Well, all depends on this initial misalignment angle that is I refer to it as theta I. And of course the energy scale of the action. So this is relatively simple to compute. So if you know these two values, you can compute the density of actions in the form of this non-relativistic field. And you can see that the main dependencies are like that. So you have that the density already expressed as a fraction of the required dark matter density from observations is like that. So you have more or less proportional to this FA, which means that it's inversely proportional to the mass of the action, and is proportional to these values of the initial angle squared. The problem is that we don't know neither the mass nor the angle. So at the end, you can choose values that give action density that is this ratio is practically 1, so you can explain the dark matter density. And for example, for values of the initial angle of the other unity, a 6 microelectron volt action will fit. Just to give some numbers, but of course, this value was selected randomly. So there is no particular reason why we should do one. There are some more details that are hidden behind this F due to the anharmonicities of the action potential. But in principle, this is stuff that can be calculated, and it has been calculated with some precision recently. You need lattice computation because this QCD stuff basically. So the question is. What happened with the value? Sorry, yes.
Sorry, thank you. I might have missed this, but what is causing the tilt in the potential? Is there something?
QCD. This is QCD. QCD effect. This is the action potential. That is basically QCD. Nothing. It's not part of the action model that you put. So this is simple, fully determined, complex calculation, but this.
Okay, thank you.
So basically, what I want to distinguish, in order to know what happened with this initial angle, we're going to distinguish two different scenarios of two different cosmological scenarios for the action, which are called the pre and the post-inflation scenario. So this means whether the value of the energy of the Pechapian scale is such that Pechapian transition happened before or after inflation. This distinguished two different phenomenology. In the case of the pre-inflation scenario, so This means that the Pichet symmetry is broken before the end of inflation, so during inflation, and is not restored afterwards in the reheating period. Then this initial value of the angle of the theta initial on the action field is unique in all the observable universe because this happened before inflation, and inflation selects one of them is inflated to all the observable universe. So this simplifies a lot the thing because you can assume that this is a single value for all the universe. The problem is that we don't know what is this value. It was selected randomly from all possible values that took place during the changing transition. So from an initial situation in which the field takes randomly in different patches, different values of this initial value, inflation selects only one and homogeneize the universe, and you have only one single value for the observable universe. In the post-inflation scenario, inflation happened before Pichet-Queen's. Pichet-Queen's symmetry is broken afterwards, and therefore the value of this initial angle takes different values in different patches of the universe. So the universe after inflation is composed by many different patches with different values of this initial angle. This has interesting consequences, but okay, let's move on only with still with the prediction of what is the expected energy density from actions due to these effects. I need to mention one more thing, that is this topological defects. The fact that the action field is an angle, it allows for these topological defects to happen, which basically very cartoon-like explanation is the following. So in principle, when this potential appears for the first time, and the angle of the action value, the value of the action field rolls down to the minimum, this happens independently in different patches of the universe. It may happen that, of course, the value of this minimum is the same in two neighboring patches, but if the initial values, which are randomly configured, it may happen that the need to connect continuously these two situations makes that unavoidably the value of the angle rolls around all the 2 pi domain from one situation to the other. These are two different spatial points in the universe, but in the middle you have a situation you cannot escape, that the action can really go to the minimum and stays in the maximum of the potential. It's topologically trapped there. No? Okay, so this is a concentrations of energy which are very high, as you can imagine, because the action cannot roll down to the minimum, at least not immediately. These are called topological defects. And okay, when this happens in 3 dimensions, these situations take different geometry. They take the shape of strings or domains, walls. For example, an action string is something that is a topological defect in which the value of the action around this string samples all the domain from 0 to 2 pi and go back to the same physical point. And the domains are walls. The walls are topological objects in which the value of the action field goes from 0 to 2 pi across the domain, across the wall. So this is a picture of a simulation. These topological defects cannot be really calculated. They have to be simulated in the computer. This is a very active area now of research. And this is a picture of an early stage of the action field in the universe, where you can see the strings on the walls, strings in white, the walls in blue, where there's a very high concentration of energy due to the fact that the action is cannot stay in the minimum and stay in other values different from the minimum. Of course, these configurations of the field are not stable. They evolve, they interact, they swing, they collide, and at the end they decay, producing an additional dark matter pollution that must be taken into account. Yes.
This is a really naive question, but can we kind of think of these axion strings as like dense in space-time, similar to cosmic strings? I don't know.
Can you imagine as what? As?
Dense in space-time? I don't know. That's sort of the way that I think of cosmic strings. I don't know if that's really correct, but yeah.
Dense.
Yeah, dense.
They have a very high energy density. So the field takes very high value, so away from the minimum of the potential. So they indeed concentrate a lot of energy. And when they decay, they produce an additional population of actions that, according to some computations, are very important.
I guess by dense, I mean like perturbations in the metric where your geodesic equation would kind of, you get a photon traveling along, it would sort of go like this at the place of the axion string. Is that the right way to be thinking about it?
I'm not sure if I understand the.
Okay, no worries. I can ask you
So,
later.
yeah.
Thanks.
So, well, this complicates things because, as you see, that the realignment mechanism is very simple, easy to compute. But of course, you have to deal also with topological defects, things get more complicated. You rely on simulations, complex cosmological simulations. And as I say, this is a very active research area. There are several groups working on this, and they are producing results that traditionally they are not all of them coincident in the importance of whether this second population of action, because eventually this topological defect disappear. They should not survive, otherwise it's a problem. This is something like this, no? They disappear. They produce another action population that is also a contribution to dark matter. They are non-relativistic actions, so they are important. They should be considered. But are they quantitative important or not compared to the realignment actions or not? This is not yet clear, and there are different results differing very much. From some people saying that they are at the same level of quantitatively at the same level of the realignment actions, to other teams that are getting something like 2 orders of magnitude higher than the realignment action, and situations in between. So this is an open area of activity. So what is important is that in the pre-inflation scenario, we don't have to care about topological effects because they are wiped out by inflation. So if they were produced at some point, they are not relevant in they are wiped out from the observable universe by inflation. So this is nice in this type of scenario. We can ignore topological effects and only use our prediction of realignment effect for action production, which is nice because we say that we know how to do this. Unfortunately, in the case of inflation, as I mentioned, this angle is unique for the universe and it's unknown. So it ends up as a free parameter. So the question is that for angles of the order of 1, you get a prediction of 6 microelectrons for the mass, but there is no reason why this angle should be 1 because it's a randomly selected angle. And you can fine tune this angle to produce practically the right dark matter density for a wide range of action masses. One could say, okay, but why would take such fine-tuned values if you want to produce the right dark matter value for a particular action mass. But in principle, this is a typical argument in which anthropic arguments fit, because in principle, in inflation, before inflation, all the possible angles were produced in the universe, but inflation take only one, and maybe it took the one that allows us to be here observing the universe. So in principle, you can apply anthropic arguments to very particular values of this angle. So this means at the end that the predictability of the scenario is not too big. You will see now that the range of masses for the action that corresponds to the right dark matter density is quite large. In the post-inflation scenario, this does not happen, which is good, but we need to deal with topological effects, which is complex. So in the post-inflation scenario, we have we can take an average for the misalignment angle, because all of them are realized in different patches of the universe. The typical size of these patches is small compared to cosmological scale. So you're allowed to do some sort of average, plug this average of the angle in the formula of the vacuum realignment angle, action production mechanism, and you get something of the order of on the ballpark of 30 microelectron volts, which is very nice. But this is not all the story, because we have to deal with the topological defects. We need to add to this contribution the computation from the topological defects, and we, as I mentioned before, there is quite some uncertainty in this value. What is nice from this model is that they provide a lower limit to the mass, because you cannot really go. This will only add more dark matter, but you cannot go to values below 30 microelectron volts, because then only the realignment mechanism will produce too much dark matter. So let me finish for today with mentioning something that is called the domain wall problem, that is related with these topological defects. I didn't mention when talking about action models that there is a very important property of models. In reality, this tilting analogy is incomplete. In reality, in some models, what is happening is not just tilting, but you have the presence of more than one minimum, more than one physically distinct minimum before reaching the same physical minimum again. And this is a model feature. So there are models with only one minimum, and then the tilting analogy is accurate. Some other models, they have more than one minimum, then you need to picture it something like that. The number of minima is called domain wall number. And if you have a domain wall number higher than 1, then you may have catastrophic consequences in the case of topological defects, because you will have topological defects in the universe with neighboring neighboring patches in which the action field has stayed on different physical minima. And therefore, in those cases, these topological defects cannot decay. They are stable, and they lead to a completely different universe that is not what we observe today. We don't see topological defects again. And therefore, these models are not clearly ruled out by observations. And this feature of the models is not something exotic. I mean, the DF, the original axioms had domain wall number 3, and the DFS models are either 3 or 6. So it's a common feature of an axiom model to have domain wall number either 1. Okay, this is what I said. This is incompatible with observations, because this topological defect would be stable. So there are two solutions to this one: to focus only on the post-inflation, on the pre-inflation scenario in which topological defects disappear, and then you don't have this problem. or in the case of post-inflation, to contemplate a mechanism for this minima to be slightly non-degenerate. So you have a preferred minimum among all these minima, and then these topological defects eventually decay. And this can be done. There are some models that are not going to decay. The issue is that it enlarges the possible values of the axial mass to give the right matter density. It pushes to even higher masses. Okay, so I think that I should probably stop here. I haven't completely finished with cosmology, but because it's an important topic, I prefer to stop here and go over this again at the beginning of more. Maybe you have questions after thinking from today.
So in this post-inflationary scenario, since the I varies in different parts of the universe, this would lead to different relic densities in different parts of the universe. Is that right?
Yes.
So then would we expect post-inflationary scenarios to imprint on, say, the CMB spectrum or the Monte-Carlo spectrum?
Yes, there are constraints on coming from CMB on this type of models.
Okay, thank you.
Have one slide on this later.
Thank you. And I may have missed this, but how do we observe these topological defects observationally or experimentally? What would it look like? So we don't see them.
Well, I think well, such high density concentration that I think the evolution of the universe would be completely different. I think it will affect anything structure of the universe.
But I mean, I guess I'm thinking that there's something that says, I don't know, how dense these walls of these strings form, or I mean, is it a constraint issue, or do these walls have a pretty severe impact on the evolution of the universe?
Yeah, I cannot answer with precision. Such this graphic picture from the homogeneous experiment, the homogeneous universe paradigm that yeah, I think people take for granted that this is.
Thank you.
What is the lifetime of these topological defects we would expect? They would have to decay at some point. Right?
Yeah, they decay. They decay. Yes, but very soon after they form. But
Is there a way
I
to
can
see?
give you a quantitative answer, but people doing this simulation, this is well determined.
Is there a way to see signatures of these decays? Like,
Well, the signature is the dark matter, the very dark matter. So at the end of the decay, reducing more dark matter.
only dark matter.
There is some discussion on whether the energy spectrum of the action population from this decay is not exactly the same as the one coming from realignment. But nevertheless, we are talking always about non-relativistic action. So I don't know if this would lead to a particular example. There is quite controversy still on the details of how these topological defects behave, their dynamics, and the final product in terms of action decay. And this is a topic of discussion at conferences. I'm not an expert. The the simulations that are needed to determine this are very complicated because the dynamic range, you need to model a large enough portion of the universe, but at the same time with a resolution where the topological defects are very good because the topological defect is very thin, very high density in a very small space. So they usually these simulations they require afterwards some extrapolation that is crazy. Many others that some people complain or that the extrapolation can be trusted. This is something. It's a nice topic right now. Yeah.
Okay, so if there are no further questions, thanks, Igor. Lunch.